So last part of the lecture for sequences. As we had done with other new topics, just want to remind you that these follow the same sort of algebraic rules. The limit of the sum of two sequences is actually equal to the sum of their two limits. So if a sub n goes to L, if b sub n goes to m, then we can add and subtract those limits. We can multiply those limits. We can factor out a common multiplier, just like we did with integrals and derivatives. And lastly, we can divide two limits. So the limit of a sub n over b sub n is going to equal to the limit of a sub n divided by the limit of b sub n. So we have the ability to manipulate these limits in the same way that we could for integrals and derivatives. And of course that makes us very happy. Or you can say that our intuition is going to be well served here. Are we okay with those ideas? Sounds like a lot of same old, same old. Are we ready to go on to the next thing? Yeah? Yeah? All right. Let's go ahead. Now, something was on 2 screens ago. It was that we say that if the limit exists, we say that that sequence converges. We say if the limit doesn't exist for some sequence, then we say that it doesn't converge, or we use the expression diverges. So what I would like to know, and this actually looks pretty similar to the homework problem that we just did a few moments ago, I want to know, does this sequence converge or diverge? And if it does converge, what does it converge to? Well, let's find out. Let's ask the question, does this limit, as n approaches infinity, does it exist? Or, another way of saying this is, what is the limit as n approaches infinity of 2n minus 1 over n? We've done these kinds of limit problems before. From the intuitive side, what do we say? Things like, hey, as n gets really, really big, what does it matter? That minus 1. So we look at this little holistically and say, oh, what we have is something that looks like 2n over n when n gets really big. We say that that limits 2. We say that the limits 2, and therefore the sequence a sub n is a word that I'd like you to yell out here.
Converges.
It converges. We are going to, this is our first time that we've used the word converges. We're going to be using the word converges all through chapter 9 and all through, chapter 8 and chapter 9. Right. We might also say that the sequence a sub n converges to the value 2, because that's its limit as n approaches infinity. So we've got some new grammar here. Sequence either converges or doesn't. And we say when it doesn't converge, it diverges. And when we say it converges, we say it converges to its limit. Mathematics here isn't hard, but getting the new grammar down typically is. May I go on to the next slide? I may? Great. Your turn. Does this sequence converge or diverge? If it converges, what does it converge to? One way we might get insight about whether this converges or similar. When n is 1, it looks like it's what? Negative. Well, when n is 1, it looks like it's 0. Is that right? When n is 1, I got n minus 1 on top. 1 minus 1 is 0. And then when n is 2, it looks like it's going to be something like positive.
I was just going to say 1 and negative 1.
I think we get something like that when we graph that out. It alternates back and forth. And as n gets really big, we're either going to have something that looks like positive 1 or negative 1. So let's go back and actually answer the question. Does the sequence converge or diverge? Wait, hold on. Let me get a coin. What do you think, Marissa? Why? They're not the same. There's not one single value that it goes to. Indeed, we say two things. We say the sequence of a sub n diverges. We could say also that the limit as n approaches infinity of a sub n does not exist because it goes back and forth between the essentially positive 1 and negative 1. Yes, Jordan.
Would you say that arithmetic sequence diverges like all the time?
An arithmetic sequence never converges unless d, the common difference, is 0.
Correct.
Okay? Would you say that the geometric sequence converges? And the answer is it does when the common ratio is between negative 1 and 1. So those are two things that you can take. Arithmetic will only converge on one instance when d equals 0. Geometric will only converge if r is between negative 1 and positive 1. Yes? That is absolutely safe to say. Sequences will only converge when the limit is a value. Should I summarize what we just said, Jordan? Okay. If a sub n is arithmetic, the sequence a sub n converges. Throw some fancy math at you guys. If and only if d equals 0. Sorry, d equals 0. IFF stands for if and only if. If a sub n is geometric, the sequence a sub n converges, and actually gets a little bit, if and only if, and it's a little bit fancier than what I originally said. It's got to be greater than negative 1 for the r, but it can actually equal 1. Because if it's a common ratio of 1, then it's just the same number all the way through. But if it's negative 1, then it's essentially bopping back and forth, and it, like Marissa had said, it never goes to a single value and it never converges. So those two things you can take to the bank. Any more questions on this slide? The bottom one, converges if and only if r is bigger than negative 1, but less than or equal to positive 1. So negative, I'll write it bigger because I know you're at a weird angle. I can also say, and it can be equal to 1. Okay, next slide. Sorry. You know what? It looks like I had a graph of it. Look at that. Clearly looks divergent. All right. What's next? There you go. Your turn. Sorry. Oh, poop. I've already given away the answer to this one. I just gave away the answer to this. What's that, Trevor? It's arithmetic. And D does not equal 0. What's the D in this case, Anthony? Okay, and in this particular instance, 2. So you can imagine that this sequence would be something like what, Candace? No. I mean, it starts at 4. Give me the first few terms of this arithmetic series. Okay. And you can clearly see that that sequence isn't going into any particular value. Okay, we're going to pick out the middle row next. All right. So, and there's the graph of that. You can. It's not going to some value, is it? I don't know how to spell that, but it goes. What's that? Well, what would we say? In the right grammar, we would say this sequence, B sub n, is divergent. Divergent. Or that the limit, as n approaches infinity, of B sub n, dn, whoa. I should really look at what I'm writing. dne. The limit does not exist. Say again, Anthony? Well, we talk about when we talk about whether a sequence is convergent or divergent. We're talking about what happens over a great deal of time. Does it over time go to a particular value?
And it doesn't run infinity as particular.
And infinity is that representation of what happens over a long period of time. All right, and that's slide 18. How about slide 19? Oh, the sandwich theorem.
Oh no.
Okay, I'll make it more palatable. Ernie sandwich theorem. There we go. Isn't some better? We are due for an Ernie's day. Okay, now. This is not the first time we've encountered the sandwich theorem. This is the first time we've done it with sequence. No. We're going to do sandwich theorem one more time in chapter 9. No, it's an Ernie sandwich, not falafel at all.
Falafel is good.
Falafel is good. All right, so what's the idea? I've got two sequences, the A sequence and the C sequence, and they happen to both be divergent, and they both happen to be convergent, and they both converge to the same value L. What's the deal with the B sequence? It has to be between A and C,